right? So we can pull those up.
Is there a way to like copy and paste?
Huh?
Is there a way to like
Yeah.
copy and paste?
Well, there is. Well, yeah, but I'm not sure.
I'll do it the fun way.
I think it wouldn't save me any time to do that. So. All right. While as you guys are getting those typed in, and maybe you're already typed in, they should be able to log in, right? Make sure you get everybody gets logged in here. Let's kind of go through the week and talk about what's happening and kind of where we're at, to summarize things that are going to be on the quiz tomorrow. Now, first of all, there's going to be a sub, right? Next 2 days. Mrs. Kinsley, okay? Great lady, doesn't know anything about calculus, but great lady. And that's, and that's fine. I mean, it doesn't matter. But you guys know what I expect on the quizzes and so forth. There will be the calculator part, the no calculator part, and to make things easier for her, number one, we won't do press the test just because we wouldn't be able to get out of press the test anyway. So, it doesn't really matter. I mean, so the stuff would be on the calculator. But the only thing we're going to use the calculator part for is like what you guys are doing on your calculator right now with those tables, where we're going to do the limit. You get the table there so you can see what's happening. We're going to talk more about that when we go over this worksheet. So that's really the only thing the calculator part is for. The other ones then, most of it then is the no calculator stuff. All right. So again, you'll get the calculator part first. To make it easier for her, let's finish the calculator part, hand that in, and then get the no calculator part. I know some of you sometimes have set the calculator part aside, maybe come back to it after if you were stuck. I mean, if that happens to you, you're really stuck on it, you want to come back later after you do the no calculator part, bring it up, tell her, give it to her, and then just say, I might want to look at that again, and I'll try to leave her a note for that. But, don't abuse that, but just if you need to, we should have enough time. I mean, last year this quiz, roughly, it should be the same length as what we did last year. And we did it on the day before Thanksgiving, which I don't think we're that far behind. I think the days are kind of off a little bit. But anyway, and that was a 2-hour early out last year. Remember, we went on the Wednesday before Thanksgiving. So the classes are only about an hour long. So I think we should have plenty of time. So that's what we're doing. Then we're going to talk at the end of the period today about 2.4 just a little bit. That's not on the quiz, but we're going to talk about some things in that section. And that'll be kind of your homework to go over that stuff. After the quiz, you can work on that a little bit, and that'll be kind of for Monday. And then on Friday, is there anybody that's going to be gone Friday that they know of? Okay. On Friday, there is that document, that exponential document that I sent to you, and there's a worksheet that goes along with that. And so you'll need that. And then there's also a solving equation practice that we need. One of the things we have to do in section 2.4 is solving equations, and so there's some practice on that. So that'll be pretty much what you work on in class Friday. You should have time in class to get both of those things done. It'll be mostly just work time on those things. So that's what's going on here. All right, so let's talk about the quiz just a little bit. In section 2.1 is when we first learned about this special limit here, the definition of the derivative. We did those limits kind of the long way, if you will. Really what that means, the long way, really just means doing this limit using algebra. That worksheet you did today with the algebra limits is really working out those limits the long way. It's taking the limit, getting it set up, and then just working out all the algebra. All right? So, we called it the long way because then in section 2.2, we learned the shortcuts. We did x cubed the long way with algebra, and we saw that the derivative was 3x squared. And so we found out, there's some shortcuts to those derivatives. So it wasn't really shortcuts to limit problems, it was shortcuts to a derivative. Okay? So when we worked out these the long way, we were really just doing algebra to find this limit. We could have done, when we had those, instead of doing the algebra, we could have just done a calculator, like what you guys are typing in right now. So we'll talk about how you might have to do that on the quiz on those problems. So that was section 2.1, 2.2. Really, that's what happened. And then we learned those power rule. We practiced those the last couple of days. So we probably won't practice any more of those today, but you can go back and look those over and so forth. Then in section 2.3, we said, let's investigate limits a little more. Okay, just the idea of limits, since it's such a big deal here. So we said, okay, this limit's a special limit, means derivative, but there are a lot of other limits. Now, I rewrote this a little differently than I had earlier on the board, because I talked with somebody who was a little confused by it. Before, under other limits, I had graphs, algebra, table. That's not just on other limits, that could be on this limit. Okay, any limit can be found by either looking at a graph, doing the algebra, or looking at a table. Okay, any limit can be done that way. So this special limit or any other limit. All right, so important to understand that. And then the last thing we talked about was this idea of a continuous function. A continuous function is a function you never lift your pencil, nice and smooth, and you can just trace and never have anything weird happen. Okay, now what's weird mean? Well, a vertical asymptote would be something kind of weird. A hole in the graph. A hole in the graph with another dot. A break. Okay, any of those things happen, it is not a continuous function. Okay, so, and then what we got into is we said these are the specific reasons why those things are not continuous. Maybe the function has no output. That would be weird. Right? Hole in the graph or vertical asymptote. Maybe the limit doesn't exist. The limit, of course, is when the cars meet. If the cars don't meet, you got a break or you got a vertical asymptote. Or it's possible that the cars do meet and there's an output, but they're not the same. That would be something weird. So those are the examples of what makes it. So on the quiz, I want you to give these more technical names or reasons why something is not continuous. So you don't have to say these word for word, but you want to be able to identify them. That's pretty much it. I mean, if you can do those things, that's pretty much the quiz. Yes?
Can I take a picture of that real quick?
Sure.
With my phone?
Sure.
With your eyes.
Um,
I don't want to think I was texting.
can you take it from there?
Oh, yeah.
And be able to read it?
Oh, yeah. You got good handwriting. It's
Okay.
perfect.
Or taking a video of me and posting it on YouTube or something, right? Like I'm making fun of Ryder or something. All right. Like there was one video, a teacher just went like crazy on an elementary kid or something. You ever see? I think it was a couple years ago. Just yeah. Well, first started just screaming at him stuff, and then like slapped the kid around. He probably deserved it. But still. Yeah, I did. Probably.
No, I work at a daycare sometimes.
Yeah, probably deserved it, but still. All right. So anyway, well, see, now I'm recording this. Now this is going to be me saying that. Trim that out there. All right. Yeah. All right. Let's. I tell you what. Let's. Now you've got those on your calculator, but let's actually look at the algebra worksheet first. All right. So one of the ways that we can do. Well, now, actually, this is for you guys. This worksheet here, I told you that I had a worksheet that had some practice on the algebra, the conjugate and stuff. So I've got a few of these up here. Now, I'll be honest, these all need common denominators, but these are actually harder than the ones we would have to do. The only one on here that would be similar to a common denominator problem would be this number 7. So if you want to take the worksheet and do that one, these you all have to factor, and they have something common, and then it's kind of, yeah, that's probably, I don't even know. I mean, I could look it up. What kind of TV show is most? And then on the back side is some conjugate practice. Now the top half you wouldn't do, the top half here you wouldn't do, but the bottom half has some problems where you multiply by a conjugate on the top and bottom. And so if you wanted to practice on those, so I've got a few copies, and if I need to make some more, I can make some more. But yeah, you're not doing the whole page, so you wouldn't get to do the riddle, so that might be another reason you wouldn't do it anyway. So, all right, so let's go to this one. Algebra limits. Now these early ones just factored pretty nicely, right? I mean, those are pretty easy to cancel. You plug them in. Number 4, there was one of them. Was it number 3? I think. Oh, and I should mention real quick on this one. If you plug in on number 2, if you plug in a -1, I think you get -2/0. But then some people factor it. Did you factor it? I mean, really, the first thing you should do is direct substitution. And if you do direct substitution, you get this. So you say does not exist. But if you factor it and cancel and then plug in, you get 1/0, which is also does not exist. So I don't care. Either one of them is fine. Okay? When you get down to this one, when you plug in, you get 0/0. Then you factor and you get, is it?
I got 12. Yeah, I got 12.
12/0, which is also does not exist. But remember, when you get 0/0, it means keep going. There might probably is an answer. Well, in this case, there wasn't. Now, I will tell you that what this means, and we're going to see it on the graphing ones here in a minute. What this means is infinity. What this means when you get 12/0, 1/0, is you have a vertical asymptote like this. And so, and why is that? Well, because 0/0 and 12/0, it really doesn't mean 12/0 or 0/0. It means this. As x gets close to 5, the top is getting really small and the bottom is getting really small. And when you divide that, what's that mean? Well, it's hard to tell. What it depends on is how fast each of those are getting small. Okay? That's what determines this. Well, we can't tell just by this alone. That's why we keep going. But then when you get 12/0, what that means is that as x approaches 5, the top is getting close to 12, and the bottom is getting close to 0. Right? Because that's what a limit is all about, is what it's approaching. Okay? So the top's getting close to 12, so let's say 11.999 divided by 1/1,000,000th. Well, what's 11 or 12 divided by 1/1,000,000th? Like 11 or 12 million, right? It's a really big number. When you divide by a really little number, you get a really big number. If the top is just a constant, like 12 or 1 or 2 or whatever. 0/0 is a different story. But if you take a constant divided by a really little number, you get a really big number. So that's why 12/0 or 3/0 or 7/0 does not exist, because basically what you have is infinity. So the cars are not going to be meeting. That's why the limit doesn't exist, because you're going to have cars going off to infinity and not ever getting anywhere, not ever meeting anywhere. Okay, so that's why it does not exist. Now, when we get to the calculator side, the calculator worksheet, it said discuss the one-sided limits. So I'm going to talk to you about what that means. It didn't say that on this worksheet because we're doing it just with algebra and we wouldn't really know for sure. So, or at least we won't study that more until we get to chapter 4. So right now, just put does not exist. Okay, what'd you get on 4 then? 5. That just worked out without even canceling or anything, right? You didn't have to factor anything. Now maybe you did and it worked, but you wouldn't have had to. You could have just plugged it right in. Okay? I think it did cancel. Okay, now you get to here. Now these are the conjugate ones. Now, 5, do we need to look at those? That'd be worthwhile real quick. 5, the conjugate's easier. It's radical x minus 3, so you need to take this times radical x plus 3. That's the conjugate. Whenever you see a radical in these problems we're doing now, conjugate is a thing to think of. So on the bottom, you just get what? X minus 9. And then here you get 9 minus x, and then I would not FOIL those out. I would just leave them. Okay? Well, those almost cancel. And we want those to cancel because the 9 here, that's what's giving us that 0. 9 minus 9. Well, we can factor out what? A negative. So if we take out a -1, we get negative x plus 9, which of course is the same as 9 minus x. Now you could take out the -1 up here, or you can take the -1 down here. It doesn't matter. Okay? So if I take it out down here, that becomes a 9 minus x, which cancels that. And now I can plug my 9 in. So square root of 9 is 3. 3 plus 3 is 6. 6 divided by -1, -6. Okay, now this one confused people more, and that's just because it was a little messier, but it's really still just a radical minus a radical. It's like a minus b. So we take it times a plus b, which means we do this. That still is a plus 12 in there, but it's this, see? So it's, here it was radical minus 3, and we changed it to radical plus 3. Here it's radical minus a radical, so we do radical plus a radical. That's the conjugate. Okay, and then we do the same thing on top. Okay, so we got x squared plus 12 and then plus square root of 12. Now on top, I would leave that alone, but on the bottom, when I FOIL that, what do I get? Well, that times that makes x squared plus 12. And then the outers and inners would all drop out. That's why we do the conjugate. And negative radical 12 times radical 12 is negative 12. And so those 12s will drop out, which is good. On the top, we got that and then all of that. Well, now the x squared's canceled. Only, though, because the 12s dropped out, right? You couldn't have canceled that x squared otherwise. You know, I see people trying to do this. They had x squared up here, and then they had x squared plus 7 down here or something. You can't cancel those x squareds. I mean, that doesn't work, all right? Only because the 12s dropped out, and we had x squared by itself down here, could we then cancel it. So now we're left with radical x squared plus 12 plus radical 12. Well, now that those x squareds canceled, we can put the 0 in, see? Because that's what was causing us to get 0 on the bottom down there. Now that the x squareds are gone, we can put our 0 in. And so we put a 0 in, and we get square root of 12 plus square root of 12, which would be 2 square root of 12 or 4 square root of 3. Either one of those would be fine. What I did there,
I mean, yeah, with the plus 7.
simple example, would be this right here. Now we know that that is 3/10, right? You cancel those 3s,
Yeah, that makes sense.
I mean, it just doesn't. Okay? You know. All right. Now what? Last two? So that's conjugate, right? Common denominator. Common denominator is this one times this one, right? So that means this one needs a 5 plus x on the top and bottom, and this one needs a 5 minus x on the top and bottom, and it makes it easier when we just have ones up there, so we have to multiply by them. But basically, the 3 over x is going to be out here. Your common denominator is going to be 5 minus x, 5 plus x. And so on top, you're going to have 5 minus x times 1, of course, and then it's minus, and then you got to make sure you get parentheses around that 5 plus x right there. So it's 5 minus x here minus the 5 plus x. Now what happens there on top? What do you end up with there? You distribute that through, won't the 5s drop out? You'll get 5 minus 5, but not the x's. What do the x's end up? Negative 2x, because you get negative x minus x. So what you have is that you have a 3 over x here, and you have a negative 2x over this. And I would not FOIL that out, but you could. I mean, a lot of times it's worse to FOIL it there. And then what happens from there? You could multiply across, or could I just cancel those x's at that point?
Yeah.
But that's what I wanted, see, because I want to plug a 0 in for x. But with that x on the bottom was making that not be good, right? I want to put a 0 in for x, but that was making it divide by 0. But now I get to where I can cancel those x's. Now I could have multiplied across. It would be negative 6x, and there would be x times 5 minus x times 5 plus x. Okay, I mean, so I could have done that, just multiply across. But again, the x's would then cancel. Okay? And now, once I cancel those x's, I can now put a 0 in for x. So I'll put a 0 there, I get 5. Put a 0 there, I get 5. 5 times 5 is 25. I get negative 6 over 25. So that's a common denominator example. There's one of those on this worksheet you could practice. Then the conjugate example up there, the other algebra ones with factor cancel. But see, this whole worksheet can be thought of as doing it the long way. Doing these limits the long way, because that's what they are. The difference is these limits are just other limits. They're not their special limit. But again, it's that same idea. All right, on this one, you just had to FOIL a bunch of stuff out, and 8's canceled, and you factored out an x and canceled it, and you get, what, 12? Like 12. Okay? So if you want to see that one when we get to the end today, we can look at it. All right. So now let's go to the calculator. So I'll give you one to practice. Riley asked for that yesterday, and that'd be a good idea to practice one more of those special limits. We have the derivative one where we do it the long way. Okay, the algebra way. We'll look at that one here in a little bit. But let's look at the calculator sheet. Now, somebody in the other class asked a really good question. Remember that one that we had before Thanksgiving? That worksheet? And somebody in the other class said, what's the difference between that worksheet and the calculator worksheet we did here? Because they had tables drawn on both of them. And there really isn't any difference. The only difference is the ones on this worksheet before Thanksgiving were all what kind of limits? They were all these derivative limits. Every one of these looked like f of x plus h. See, we got sine of 3 plus h, we got 2 to the 3 plus h. Every one of these, all 6 of them on this page, had that special look to them as h goes to 0. They were all derivatives. And so we were identifying that way. Now, I'm not going to ask any questions on the test where you have to, what function was it, and so forth and so on. But I do want you to understand that those were just limits, and they were these special limits. And what you did on that worksheet is instead of doing them by algebra, we did them on our calculator with a table. Because, quite honestly, there's no algebra you could do on this one with that sign. There's no algebra you could do on this one that would make things cancel. So sometimes, now on 3 here, what could we have done on 3? Yeah, we could have done a conjugate on 3, right? See, so I really want you to, I sometimes feel like some people look at these problems and they think, oh, if it's this certain way we use a calculator, if it's this certain way we do algebra, if it's this, like they're different beasts. No, this one right here we did on our calculator before Thanksgiving. We could have done conjugate method on this one right here and gotten the same answer. Okay? This one down here, we could have foiled that out. Been an easy one. We could have just foiled that out and gotten that answer there. H's would have canceled, right? But we did it with a calculator. So it just depends what the directions are, which one I want you to do. Okay? And just understand they're really the same thing. All right, so this page is just a bunch of limits that aren't the special ones. They're just some limits I want you to use your calculator to get. But like this one right here, we could have done this on a calculator. We could have done algebra on this one, I bet. I bet we could have foiled that and canceled some things, right? Or factored it and canceled some things. We could have done conjugate right here on number 1, right? But I put these on here and said, hey, let's do these with the calculator. Show a table. So understand how that works. Not only that, but aren't some of these, I don't know if any of you noticed, aren't some of these actually the special limit? Aren't some of these actually the definition of derivative? Except they don't have an h in them. They have an x, right? But isn't that what we did when we went to type those in the calculator? We took the h out and made an x there so we could put the calculator. So that's really a derivative right there. I mean, not that you need to recognize that. Number 3 is. Okay? That's probably the only other one. Well, actually, I think this one is too. This would be 0 plus h. Okay, so I think that's actually one too. But anyway, so if you recognize those things, that's good. You're getting the hang of it. All right, so number 1. Who had number 1? Steve, right? Now, okay, you did something very bad. Horrible. Very, very bad. Terrible, terrible. Go into F1. What did he put in F1? I hope you didn't do all these like this. No. Go. Yeah, go arrow over to your. Click here in the graph. There you go. Now hit Tab. Tab. Go up to F1. What did you do wrong here? You put the limit in there. Put the limit in there. What's he supposed to put in? The other stuff, not the limit, right? We're graphing that, and then we're looking at the table to see as x goes to 0. Okay, so can we delete that limit stuff? Or we can just go there. Okay. So my idea was we would do this to save time.
Good try.
That's all right. There we go. All right. So on the quiz tomorrow, if it's a calculator page, now just so you know, the instructions will probably say evaluate the limits using table, justify your answer using tables, graphs, or algebra. I mean table. If you're using your calculator, use the table. I mean, because you can't really draw a graph by hand that really shows this is what the limit is that well. Okay? This just shows it. Let's just do this. Do the table. And if it's a no calculator one, you're probably doing algebra. Unless I've given you a graph, then you're just looking at the graph to get the limit. Okay, I mean, so even if the directions say justified by this, I mean, it's just pretty obvious which one it is. So copy this table, all 5 of these things. Although I will say, we don't care about this row, right? We don't care at all, and you'll see in some later ones here, about this row right here. We only care where the cars are meeting. And on this side it's 0.5, and on this side it's 0.5, so the answer is 0.5. Now, the window, the neat thing about the graph here is you can also, since you've got the table and the graph side by side, you can certainly see, now his scale is actually nice. You can see, we got to see that's a 1 up here, and this is 0 down here. So right here is 0.5. So there they come. The cars are meeting right there at 0.5. Okay, so there you go. That's the answer. Okay, who had number 2?
When we write our table, you still want to put 0 undefined.
Yeah, go ahead and put that in there. But yeah, put all 5 of these, both columns, copy it down. Now, I like 3 decimal places, but isn't it pretty clear it's exactly 0.5? So if it's exactly 0.5, you don't need to put 0, 0. You can just put 0.5. But there are going to be some other ones where we'd have to go to 3 decimal places. Okay, who is next? We're going to find out if this is faster or not. Who? Because right now I could have Steve, although the rate he was going, I don't know. That's fine. Okay, Carrie's got it here. Now, this yellow thing that shows up can be very helpful when you're in those different columns. Okay? And sometimes it can be just a pain and get in the way. Okay? So arrow down a couple there, Carrie. And yeah, go right in there. Okay, so it looks like they're meeting at negative 0.416, and that turns out it is. And if you look at the graph, sure enough, and now most of these on this page are as x approaches 0, okay? Except for one, it was x approaches 3, but that's fine, okay? I wish I wouldn't have put so many that was x approaches 0, so you know that it won't always be 0. The special limit will always be 0, right? H will always go to 0, so the 2 points become 1 on the slope, right? But on other limits, who knows what it might be. But look right here. Sure enough, it looks like the car's meeting down here at about negative 0.4 or something, whatever. This seems reasonable. Okay, so that's that one. So there, John, to answer your question, would be 3 decimal places. Okay, number 3. Who's got that? Other care. Care, is this in any kind of order? This is working. This is working. All right. Now, oh, look at those points. That's I don't know what happened. All right, you're in your thing here. Go to window here. Go to window and just go to zoom. Those of you that have got other ones to do here, let's go to window and just do a zoom standard. Click on your graph screen and do a zoom standard. There we go. Okay, so we look at this and it looks like 2.718, right? They're coming in here on both sides, seem to be approaching 2. But now, go over and click on your table. Now, everybody listen to this. This is very important. It's going to come up on a couple of problems here. Whenever your number here goes off the cell, out of the cell, you should put the thing on there to see if it's in scientific notation. Because I told some people wrong this morning that were in here. Sorry, yeah, it might have been you. I don't know. It was some other people too. I don't remember you or not. But this one is fine. 2.718, 14598. Okay. So on both sides it seems, and you look at the graph, sure enough, it's coming in here. The cars are meeting right there, 2.718, whatever that number is. What, by the way, what is 2.718?
E.
Good job, Brittany. That's E. Everybody know that? I can't believe how many people are not knowing it. 3.14 is pi. 2.718 is E. Okay. All right. Next one. Italian. Okay. All right. What's happening here? Now this is the one as x approaches 3. What'd you say on this one? Does not exist. Now, just look at the table for a minute. On the left side, you're getting negative 50,000, basically. On the right side, you're getting positive 50,000. What's that mean? It's infinity, right? It's infinity. If we were making these numbers a little closer to 3, like 2.999, more 9, this would be 50 million instead of 50,000. but then the graph shows it too. As x gets close to 3, boom, positive infinity, negative infinity. Now, here's where you should have had something extra on your, we didn't talk a lot about this, but on, what number was that? That was on 4. So here's what you should have had according to those directions. And there might be one like this on the quiz tomorrow when you're doing limits. And it would be on the calculator one. If it says, if the limit does not exist, check the one-sided limits. Because let's face it, why does a limit not exist? Think of the cars. They don't meet, right? So what you're doing when you say the limit doesn't exist, what you need to do when it says check the one-sided limits is tell me why they don't meet. What's the car on the left do? What's the car on the right do? So what we're saying here, and what you would do is you'd say, okay, the limit as x approaches 3 from the left was going to negative infinity. And the limit as x approached 3 from the right was going to positive infinity. So what you've just done there now, in chapter 4 we'll do a lot more of this, and I'll be very picky about this, okay? But for now, if it's on the calculator one, it's all the information you need right there in the table. It tells you where the car on the left's going, where the car on the right's going, okay? But when you give your answer, don't say the car on the left. There's a car on the left. Okay. So, like on the AP test, they think you're crazy or have a crazy instructor. Which could be true. So you go, as you approach 3 from the left, it goes negative infinity. Approach 3 from the right, approach positive infinity. So the cars don't meet, so the limit does not exist. Okay. All right. So back to that. Okay. So again, clearly it shows that right there. So that's what it means by check the one-sided limits. All right. Next.
Me.
All right. And on this one, as x approaches 0. Now again, this one you can tell that scientific notation e negative 5 means what? Really small, right? So 0. And clearly we could say as x is approaching 0, look what's happening right here. The y value is approaching 0. So there it's from the negative side, there it's from the positive side, but they are meeting the limit is 0. Okay? Stop me if you got questions. Next one. All right, now, again, the graph being right next to you can certainly help. But what do we got here? Why is that not showing me the yellow? Arrow up. There, now it does all of a sudden. So it seems like when you arrow around, but now we can tell, okay, that's a really big number. That's like 3 million, 33 million, whatever. Clearly, negative infinity on both of those. And the graph shows it. Okay, so this would be another one, does not exist. And then you would do the two-sided, the one-sided limits. From the left, negative infinity. From the right, negative infinity. Now, they're going the same place, but they're never getting there, right? So they're not going to meet. Okay, they're both going negative infinity, but they're not going to meet. All right? So again, technically that does not exist. Limit does not exist. Okay?
So
All right.
What point is it of the number where you know?
Say it again.
At what point is it going to be a very leading number where you know that?
That's a great question. The graph certainly shows that, but yeah, I mean, you get any even number in the thousands. If you're going 0.0001, it depends how small that number is. You're in the thousands, yeah, it's infinity. If you're not sure, make that number even smaller and see if that number keeps getting bigger and bigger, and then you know. Okay, next. All right. All right, this is a great one. I love this one here. Okay? What is the answer to this one? Why isn't it 1? We don't care about this one. Remember we said that earlier? The fact it was undefined didn't matter? Why is it? Where is a picture of this over on the board over there? Number 3. What we have is the cars coming in here and meeting at 2.718. Look at the graph. Look at the graph right there. That's meeting at 2.718. But at 0, we're getting a value of 1. So we're getting this output. We don't care about that. The limit is where do the cars meet. And so in our table, these are the values we care about, not this one down here. Most of the time it's undefined, so we ignore it kind of anyway. And sometimes there's one, isn't well, we'll get to it. There's one that it's going to be the answer down here, but it's because these are still meeting, but there it's not. Now, I'll be honest, I really don't think this is a value of 1. It's a limitation in the calculator. It's confused. It doesn't know what to do. Because look at this function right here. Put a 0 in for x right here. What do you get in the parentheses? 1. What do you get on the fraction?
1 divided by 0.
You get 1 divided by 0. So what the calculator's trying to figure is what's 1 raised to the 1 divided by 0? Well, how can that be 1? 1 divided by 0 is undefined. But then again, what's 1 raised to anything? 1 raised to anything is 1. So the calculator's saying, oh, we got 1 raised to something, so it'll be 1. But it's 1 raised to basically infinity. What's 1 raised to infinity? You see what I mean? So it's like this, ooh. It could still be 1, okay? It could, but it's really more the limit. It's approaching 1, maybe. Well, it's not. It's approaching this right here. It's approaching 2.718. So I think, matter of fact, go to the calculator side. Who's doing this? No one. Go to the calculator side. And just type 1 raised to the 1 divided by 0. My guess is it's going to give us 1. Okay? Look what it says down here. It says 1 to, it's a warning, 1 to the infinity or 1 to the undefined is being replaced by a 1. So it's not really saying that it equals 1, because it really doesn't. Okay? But it's saying, okay, because of the programming of the calculator and the way we're calculating these things, this is what it's going to tell. Okay? So, all right, back to the calculator side. So anyway, that's a really good one to look at. The table tells us it's 2.718. So does the graph. Okay, that's where the curves meet. So the limit does exist. Everything's good. All right, next one. This one? Okay? Now, this one, 1.414, and we have no problem there, and that's where it's meeting, and so that's the answer. Actually, this one, couldn't we have easily just done by plugging in? I mean, if you look at it, you put a 0 in there, 0 minus 2 is negative 2. The bars would make it positive 2. Square root of 2 is 1.414. There it is. Okay, so there's nothing weird happening on this one at all. Okay? Yes?
I don't think I, this morning, how do you do that?
It's next to the 9. The template there, the template button next to the 9. Yeah. There is a vertical bar somewhere else, but it doesn't
Yeah,
mean.
see, that's what I was reading.
Yeah, that one doesn't work. That one doesn't. You can also type ABS parentheses and then put it inside, and then that's absolute value as well. Okay. How many we got left? 2 more? Who's next? Who's I am?
Samuel. Sam.
All right. Now this was the one I told you wrong. And John, were you in here and we graphed this one and we zoomed in? And what did we say? Did we say does not exist? Did I tell you we said does not exist? Or did I say 0? I said 0. 0's right. 0's right. But here's where I was getting confused and I was being stupid. Right here, so you get negative 3.056, so you'd be tempted to put negative 3.056. But then if you make these numbers smaller, which is what I did, then it was like negative 4 or something, and negative 5, and it was bouncing around all these different values. Well, I was being dumb. Arrow up. There one, Sam. Okay, this is what I didn't do. Okay, when you arrow, well, not that far. But, okay, there you go, now just one more. Okay, see the E negative 5 out here? It's a small, it's getting close to 0. It's 10 to the negative 5th. Okay, so when you see that number fill in the space with the dots, be sure and get there where you can see the L so you can see that that's actually getting closer and closer to 0. So on both sides, that's what's happening. So it's scientific notation. So, and again, the graph is a little harder to tell on this one because if you zoom in on this, this thing's just bouncing up and down like crazy. It's really a weird function. Okay, it just, and the more you zoom in, the wilder it gets in there. Okay, and you keep zooming in and keep zooming in, and it keeps doing it. So, but it is approaching 0. Okay, last one. And this is kind of a good one, too. Who's got this one? All right. again, if you've got a nice window, you can see on the graph, as x approaches 0, are the cars meeting? The cars are not meeting, so the limit can't exist. Look at the table. On this side, it's negative 0.5, and on this side, it's positive 0.5. So on the left, this car is coming in here at negative 1/2. On the right, this one's coming in at positive 1/2, so you could write both of those down. The limit on the left, negative 1/2, the limit on the right, positive 1/2. The limit does not exist because the cars don't meet. And so the graph shows it very nicely, just like some we've been doing, but the table also shows it very nicely too. Negative 1/2, it's approaching there, positive 1/2, it's approaching there. Okay, limit does not exist. Okay, but on the quiz tomorrow, it's calculator 1, copy the table, and you would say does not exist, even though you can tell it right here, 2 on the graph, but put your table down. All right. Well, that's good stuff, because really in looking at all that, we've really looked at graphs and how we can see cars meet, don't meet, does the limit exist, does it not? We've reviewed the algebra techniques we need. We've talked about how to do it on a table. So all of those limit type problems would look something like that. So let's have you practice this problem right here.
She's a distraction. Oh.
Hi, honey.
Hey, honey.
Oh. I knew that would just creep him out. All right, so kind of creeps me out. All right, so all right. So, oh yeah, God, but that on video too, man. Jeez. Well, luckily she won't be watching it. She won't be watching it. I even tasked her on the weekend to say, hey, you want to go on YouTube and watch one? Okay, so, all right, let's do this problem right here. Let's see, I think I did this problem. Here's f of x equals this. You find f prime of 3 using the definition of the derivative. All right? And let's say this was on the no calculator part of the test. No calculator part of the test, and I say, here's this function, find f prime of 3 using the definition of the derivative. Go. I'm going to start writing some stuff up here, so don't look. All right. Now, see? Exactly. You really think you'd get that excited about a right answer this week? Oh,
Oh, no, I got it.
I don't think so. I mean, discrete math's great. I mean, it's good. If I was you guys, I'd take both. But you don't have room in your schedule. Math nerd. You don't be a math nerd. You know, full day of math class. All day long. My dream high school thing. All right. I did actually go to my math teacher and try to do an independent study math class. But not, I know you won't believe me, but not because I'm a math nerd and proud of it, but because I wanted to get out of English and take that. I wanted to get out of English. I thought I could quit. And I thought my math teacher would definitely be in favor of that. Surely he would see the reasoning for not taking English. And he said no, he wouldn't let me. He said English was too important. I need to be able to write in college and stuff. Still not speaking English.
Was he right?
Well, he was right. Yes, he was right. And he knew I was wanting to do that, knowing an independent study, I wouldn't have to do that much, and I'd get out of English. All right, so the answer is 8. And we knew we could have known that because the shortcut told us, right, that f prime is what? Plus 2, and then plug a 3 into that. 2 times 3 is 6, plus 2 is 8. So we kind of knew we were going to get 8, or should have known we were going to get 8 anyway. All right, but now, here's the other part I want to add to this. I haven't asked it this way, but if I ask it, this is the part on the quiz where if you really understand these things, I may ask some of these questions in a little different way. If you really understand what's going on with limits and what we've been trying to summarize here, it shouldn't be a problem. But let's say this same question was on the calculator part. Let's say the same question was, use your calculator and a table to find f prime of 3. So I gave you these same 2 pieces of information in red and said, use your calculator and a table to find f prime of 3. Tell me what you would do. What equation?
2x.
No?
The x.
Oh, I'm sorry. Okay, I would say use your calculator and a table using the definition of the derivative to find f prime of 3. Okay? Using the definition of the derivative. But what equation?
That's into
This? No.
the.
In the top right.
Okay? What you would do is you would say, okay, I got to use the definition of the derivative, which is this, and then f of 3 plus h means put 3 plus h in where the x's are, put 3 where the x's are. I would get to here, and instead of, now, and understand this, all we did when we got to here was set up a limit. What are the ways we can find limits? Graphs, algebra, table on the calculator. Well, the way we did it here, and the way we've been doing it, was just using algebra. So that'd be on the no calculator part, so we did the algebra way. But you could also do it as a table on your calculator. So what we would do is take this limit we set up, we would type it in, but instead of h's, we would do x's. Somebody do, Zach, did you do that already? Okay, so let's go to Zach's calculator. You're probably still on here. Okay, and so he went into F1 and he put that whole, go ahead and hit a tab so we can see your F1. Okay, so then arrow across there. So he's got, instead of h's, he's got x's. So 3 plus x squared plus 2 times 3 plus x minus 3 squared plus 2 times 3, and then all over x. So take out the h's, put x's in their place, look at the table, and sure enough, 8. Does that make sense? I mean, it's just two different ways to do that limit. Okay? So we set up the limit on paper using the definition of the derivative, and then instead of going the algebra route to solve it, we go the calculator route to solve it. We just plug it in and we see what it is on the paper. Either way, we get 8. And then, of course, there's also the shortcut way of finding what f prime 3 was, using our shortcut rule, plugging a 3 in, and we get 8 down. Okay? All right. That's it. I mean, really, if you understand those things and you can do that stuff, the calculator, the algebra, look at the graph, the only thing we haven't done today, and I want to take a little time here to talk about section 2.4, but the only things we haven't done are what we did the last 2 days, which was some practice on those power rule, and you can go back to section 2.2, there's some of those where you can just practice those, bring the power down in front, subtract 1 from the power, that kind of stuff, so we did a little bit of that on there. Looking at these graphs, if you look at page 110, they have this graph section. 13, let's see if I go to the camera here. Sorry, those people that are watching the video aren't going to see this, but on page 110, we had this section here on 13 through 26 using this graph right here. Okay, find these limits. I mean, I think a lot of you thought that was pretty easy, just, do the cars mean or not? And then that's also that stuff over there with continuity. Why is it discontinuous at these various places? Well, here's some you can practice right here. Some people in the air class just came up and got the solutions manual, copied these down to review this. Do section 27, numbers 27 through 36 on page 111, just to practice some of those. So those would be some more graph ones. This graph practice on doing limits. Okay, and really, that's the whole thing. All right. So what I'd like to do, finish up here, and then it should leave you 15, 20 minutes or so to practice for the quiz or whatever, is look at a couple of ideas that are in section 2.4. Okay? So you might want to get your notes out or something where you can jot some things down here. And so section 2.4 is where we say, okay, let's begin the process now of what we learned in chapter 1, which was essentially the chart and all the connections between f and f prime and local max, local min, stationary point, that stuff. And now what we're beginning to learn from chapter 2, which essentially is those shortcuts on derivatives, how we can find derivatives by these shortcuts. Now, so the rest of chapter 2 will be more shortcuts, more rules for derivatives. Chapter 3 will be all about different rules and stuff. And then along the way, we'll be showing how can we now solve some problems. So we're just getting close to where we can actually start doing stuff with what we're learning. Okay? So there's 2 things that I want to mention. The first one is, when we have the chart, we had f prime, f double prime, right? Those connections. So if you do the derivative of f, that's f prime. You do the derivative of f prime, that's double prime. We could keep going, but usually those are enough. All right? So now the question is, that's doing the derivative. So now the question is, what's it mean if you go in reverse? And I mentioned that term already. The antiderivative. The antiderivative is when you go from f double prime to f prime, or when you go from f prime to f. That's called the antiderivative. Now, we actually did that with some graphs. If you had an f prime graph, we drew an f graph. Now, the only thing about that is when we went from an f prime graph to an f, what didn't we know? Where it started, right? Well, there was a whole bunch of different f graphs you could have for an f prime graph. So there was this whole vertical shift. So to give an example, let's say we had x cubed. We know f prime would be 3x squared, and we know f double prime would be 6x, okay? So now the question is, can we go the other direction? Can we do the antiderivative, okay? If we started here with 6x, could we know that our antiderivative would be 3x squared? Well, yeah, we know if it's x to the first, we don't go in the opposite direction. There should be 1 power higher, right? So we know if we have 6x, we would guess that it must be 6x squared, right, at least. But it's not 6x squared, it's actually 3x squared. So how do we make that 6 into a 3? You divide by the actual power. Now think about that. When we do a derivative, we bring the power down and multiply, and then we drop the power by 1. So in reverse, we ought to what? Raise the power by 1 and divide by that power. So it kind of makes sense that we would raise the power to a 2 and then divide by 2. Sure enough, we get 3x squared. And the same thing should happen here. We should raise the power by 1 and then divide by that new power. And sure enough, that's 3x squared. So what would be the next one up the chain? Well, no, we'll get to what we call it in a minute. But wouldn't it be 1/4 x to the 4th? Right? We would raise it up to a 4 and then divide by the 4. And sure enough, you can tell by doing the derivative. Bring the 4 down front, it would cancel the 1/4, and we'd have x to the 3rd, right? So that's just kind of reverse. Not that big a deal right now, but I mean, simple ones we should be able to do. But then the question is, what do we call it? Yeah, F antiprime. What kind of thing do we do there? A German short hair maybe, or I mean, I don't know, or the other direction maybe, you know? Well, there'd be this vertical shift kind of thing. In other words, yeah, if you had started with x cubed and wanted to draw the antiderivative, right, it would have a certain shape, but it would be, we don't know where it would be for sure. For example, when we did that antiderivative, couldn't there have been a +7 right here? What's the derivative of that right there? Isn't it still x cubed? Because what happens at +7? It goes to 0. Or what if this was 77? It's still x cubed, right? So anytime we do an antiderivative, what we'll do is we'll do 1/4 x to the 4th plus c, big C for some constant. Okay, and yeah, we'll talk more about that later. But anyway, that would be it. Now, what do we label it? Well, there really is not going to be a symbol for that. What we're going to do, and this will affect some of you, because I noticed on some of you when you talk about function f, you've been putting capital F or an F that kind of looks sort of like a capital F. That's what we're going to use, capital F, for the antiderivative. So big F is the antiderivative of little f. Now, so then the question is, what if you do the antiderivative of big F? Bigger F? Yeah, I don't know. No. Well, we won't do it. We won't do it. I mean, typically there's no need to do, if you have a function, there's no need to do its antiderivative more than one time. Now, what if you start with a function that you've labeled big F and want to do it? We won't do that. I mean, we just won't do it. Okay, so, but we do want to reserve then capital F to mean the antiderivative of little f. Okay, and so big F prime, following through with this, big F prime is the same thing as saying what? Little f. So from here on out, a lot of times we'll be saying little f and big F. Okay? So big F prime is the same as little f. Those are the same thing. Yes. Absolutely. Yes. The second half of calculus, integrals, that thing we do with area and integrals, actually are all connected to antiderivative. Slope is kind of derivatives, and area will show how that happens is actually connected to antiderivative. Okay? Yes, Steve.
What's like the notation for this, like derivatives is d over dx instead of antiderivative?
There is not an antiderivative notation right now for antiderivative. I mean, like a dy over dx. Actually, the integral symbol, I think some of you have seen it maybe on your calculator, that symbol right there is actually, that's integral really, but it can mean, depending how it's written, antiderivative. So that would be a symbol we use, kind of this S-shaped curve. Okay? But again, that's way down. All right, so anyway, this idea of antiderivative then is just going in reverse and doing the derivative, okay? What kind of problems can we solve with this? What can we actually do with this information? Here's what we can do. First of all, we need to write down a fact. This is on page 112, okay? Global, we've talked about global or absolute max min values already a little bit. Okay, so we're going to start with this fact right here. Global max min values of f, some function f. Let's see. Can occur only at stationary points of f or endpoints of f. Now, what's a stationary point? Where f prime equals 0. Now, technically, that's not complete. Technically, global max min values of f can occur only at critical points, which means where the derivative is 0 or undefined. But we're going to ignore undefined for right now. We won't deal with functions that are undefined and messy. We'll get into those later in chapter 4. Okay? But for right now, where the derivative is 0, so think about it. If I want to find a max of a function, here could be a function right here. There's a local max right there, but where is the max value of the function? At the right endpoint, right? Now, if I have another function that just goes like so, now the max is right there, where the derivative is 0. About the only, and the same thing would be true with minimum. Okay? The only, in this problem, looks like the lowest value is down here at the left endpoint. In this one I drew, it looks like the lowest value is down here, where the derivative is 0, at a peak, right? So it makes sense that the low points or the high points can only be at an endpoint or at where the derivative is 0. So we're going to be really interested in where the derivative is 0. Okay? So we're going to take this problem right here. I want to take a piece of paper, rectangular piece of paper, and we did a problem like this. You didn't do it, but you looked at it on one of those very first documents I sent to your calculator. Way at the end of one of the last pages, remember it had that box and you could drag that slider and it made the box get taller and whatever. And what we wanted to do is what is the maximum volume of that box. What I wanted to do was I wanted to cut out corners, square corners, all the same size, and create a box. So the question is, what size corners should I cut out to create a box with the maximum volume? Well, first of all, we need a function for the volume. Well, what's the volume of a box? Length times width times height. Now, let's make this particular piece of paper 10 inches across and 8 inches that way. Now, what I don't know is how big of a square I want to cut out. So we'll call that x. Okay? Now, when I cut out those squares and fold up those edges to make my box, what's my length going to be? Which would be across, which wouldn't this be my length right here? Wouldn't that be 10 minus 2x? So my length is going to be 10 minus 2x. This is where we start to put together those story problems we did in the appendix with the calculus that we can actually now do. Okay? So what's going to be the width, which would be this distance across here? 8 minus 2x. And then what's going to be the height of my box? X. Right? When I fold those pieces up. So that's going to be the volume of the box. Now, what we did on that calculator document is they had a graph of volume, and you scrolled along to see where the max volume was. But we're not going to do a graph. We're going to use our calculus number. Okay? So, we're going to cheat a little bit. Now, normally, just because of time, normally we would then FOIL this all out, and we would get our volume equation. Okay, we're going to go ahead and let Zach cheat for us on the calculator here. And go to the calculator side, and go to Menu, Algebra, Expand. We won't do this very often because usually we'll be doing this by hand. And then type in that function there, 10 minus 2x. Well, you're not inside the expand parentheses anymore. There you go. We're gonna need another set. Hit a right parenthesis. No, you hit a left. Delete that. No, stay inside. Hit a right parenthesis right now. That didn't do it? Okay. Now you better go to the 10. I thought maybe if you hit a right, it would do another principle. Hit a left. There you go. Now a left. Oop, 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 oop. Stay in. There you go. Now hit a left. There you go. Now 8 minus 2x. And then x. I don't think you need a time sign there when it's on the back side of the parenthesis. If you ever have an x and then a left parenthesis, you have to put a time sign there because it's going to think it's a function. It's going to think it's x of something. Okay, but I think on the back side we should be fine. Hit enter. Okay, and there we go. So it expanded it out for us, so we just kind of cheated there. But so there is our volume equation. Now, back to what we said here. Global max and min. Now we're interested in max, right? We want the max value, max volume. So we want the global max value, not of f. We want the global max of what function? What's our function called? No, it's not f. V, right? We want the max volume, volume V. This is volume. We have the max of the function V. Okay? So the max of the function V can occur only where, V prime is 0, right? The max of V can occur only where V prime is 0 or at the endpoints of V. Well, first let's talk about endpoints. Now this is something we'll have to talk a lot about later on. But the endpoints would be the littlest and biggest that x can be, right? Those are our endpoints. Well, what's the littlest that x could be? X is this piece we're cutting out. Littlest x could be 0. Now what would the volume be then? You wouldn't have a box, and so the volume would be 0. So that's clearly not a max. That's the minimum volume, which we're not interested in, but that's what will happen there. So we know our max isn't going to occur there. Now what's the biggest that x could be? Isn't it 4? Because if x is 4, you take half of this side, and then this would take the other half of that side. You couldn't be any bigger than 4. So it looks like the littlest and biggest that x could be in this problem is 0 and 4. So those are our endpoints. And would we have any volume if we cut out those bigger pieces? No. So there'd be no volume at either one of these. So those are actually our minimum. So our maximum must be somewhere in between. Okay? Well, that must be in our other possibility. The max value of V can only occur where V prime is 0 or at the endpoints. Well, the max is not occurring at the endpoints. The min is. So the max must be where V prime is 0. Here's where we can actually use what we've learned. What is V prime? And then we set that equal to 0. And you are going to do this. This is the first time now of many times this year you are doing this. Matter of fact, many times in these problems, I will say, hey, if you don't know what to do the derivative, set it equal to 0, because that's a great place to start. Stationary points are a big deal. In the chart, they were a big deal, okay? And so they're a big deal. So we do the derivative, we set it equal to 0, and that is going to be, well, I erased it, but those peaks and valleys, that's going to be where our max is going to be. So where does the derivative equal 0? This is why on Friday you're going to be doing a worksheet on solving equations, because you're going to have to be able to solve these equations. Now, this particular one I don't think factors. If this was a no calculator problem, we would be factoring now at this point and trying to solve that way. If it's a calculator problem, you would still have to have this on your paper. But we could now go, and Zach is going to go ahead and solve this one for us. So you would have to have this on your paper, but then you could go, you have to go to solve first. What do you got? Go to menu, algebra, solve, there you go. And now we're going to type this in. Okay? So this is going to give us our stationary point. Now we're going to talk, not today, but we'll talk next week about, and then he hits comma X, right? And hit enter. And that's no good, so let's do control enter so we get a decimal because we'd rather have it. Okay, so it gives us two answers, which quadratics often do. And what do you notice? Yeah, it can't be the second one because that's outside of our endpoint, 0 to 4. So it must be that one. So X, our stationary point is 1.472. That must be where the max is. Now we'll have to do a little more to show that that's actually the max. And what we would do is we would take our 0 and our 4 and our 1.472 and plug them back into the V equation. to see what those volumes are, and clearly the biggest volume is gonna be the one that's here. And so what's that mean? That's the size, that's what X is, that's the size of square we should cut out. If we cut out that size of square from each of the four corners, we are guaranteed then to have a box with the biggest volume for that size of piece of paper. So we can actually use what we've learned about the shortcut of a derivative, match it with chapter 1 in the chart, and how that tells us stuff about maxes, and solve the problem. Remember the snowmobiler stranded and wanted to get to that, right? What's the minimum time it will take him? So we wrote a time equation. Here we wanted the max volume, so we needed a volume equation. You want the minimum time to get to the gas station? Write a time equation. That's what we did in that problem. Then we would go to this step. Do the derivative, set it equal to 0, find when that min and max would be. Okay? All right, so have not really hit very hard on this section 2.4 stuff. Tomorrow after the quiz, your assignment will be, really for Monday, is the 2.4 homework questions. You're not going to be able to do all of them. They won't all probably make sense. But a lot of them probably will. But just put in some time looking at them, okay? Do them, because then at some point next week, your assignment will be to finish all of 2.4, so whatever you have done would make that much less you have to do. So that way you can see what questions you have, which questions were on there you didn't understand, and that'll be part of our discussion in next Monday or next week, okay? So quiz tomorrow, then you'll have these 2.4 homework questions after Monday. On Friday, we'll have a calculator activity that I sent you the other day, some solving equation review. If you know you're going to be on Friday, you need to pick up those worksheets from me, okay? All right. That's it. You've got the last 10 minutes, I guess, to relax. But the quiz tomorrow, that's your main thing to worry about. I've got these practice algebra things if you want them. There's a few on there you can do that could be helpful maybe. Remember, I will not be here in the morning. So